Okay, we're going to start our announcements now, and I have quite a few of them since I haven't been able to announce anything since May. So get your seat belts on. Tonight's speaker, that was it, Michael Foggia. I'll do a real introduction to you a little bit later there, Michael. He's coming all the way from Portland. So, as you know from previous meetings, I always talk a little bit about the climate. We have a Category 5 hurricane along our east coast. Someone on the news said 2 or 3 days ago that this is the 5th Category 5 in the last 4 years, and I thought, wow, I didn't know that. So, of course, I then went to the International Energy Agency that has a lot of data, and I thought, I'm going to plot this up since 2000. So this is worldwide. Category 5 hurricanes is on the increase. Category 4 hurricanes is on the increase. Category 3s are dropping. Some of them must be turning into 4s or 5s. 2s are dropping. 1s are dropping. So what's the overall story? All tropical disturbances globally are dropping. Since the year 2000, we have about 30 fewer tropical disturbances globally. So that's curious. We're having more Category 5s and Category 4s. These are the Category 5s from 2000 to 2018. For the first 16 years, we had 8. For 16, 17, and 18, those 3 years, we had 4. Throw Dorian in, and we've got 5 over the past 4 years, and of course we're not done yet this year. The reason, when I first saw Dorian way out in the Atlantic, I thought, my gosh, that has a long path length to get to the States. There's a lot of warm water out there. Look at this increase in temperature just since the 60s. It actually mirrors the atmospheric increase in temperature pretty closely. That's about, it's over a degree, maybe about 1.4 degrees. So if we have a long flow path length for a tropical disturbance, you can guarantee, I think you can put some money on it's going to be a bad storm. Now I want to talk about where we're at in climate solutions. You may know that I along with some colleagues, got the approval of the Board of Directors of the American Institute of Chemical Engineers last October to form the Climate Solutions Community. Well, it takes a long time to get something done at a global level, and headquarters has a lot of things on their plate. So it's slow. So I and several colleagues locally, not all chemical engineers, there's a physical chemist, a couple of petroleum engineers, and there are 12 of us to start with. Now there's 18. We formed Climate Solutions for Texas. I'll tell you a little bit about what we're doing. An engineer from Nigeria came to a workshop, Climate Solutions workshop in New Orleans at the spring meeting. He went back and started Climate Solutions for Nigeria and is seeking government approval as a non-governmental organization. In July, I attended a Carbon Management Technology Conference in Houston, met an engineer from Illinois who just had an urge to do something about climate change. On his own dime, he came down. He's sort of a semi-retired guy. My wife and I happened to go up there in the Chicago area in August because my wife is from there, and I met with him, and he is forming Climate Solutions for Illinois. We're going to have an October 2nd Climate Solutions session at the Southwest Process Technology Conference. What I want to point out here, Mark Harkness and I are the chairs. Oh, by the way, Dennis Griffith said to tell everybody we used this venue years ago, many times. And I didn't like the walk from the front door, but I've been told that there's a door on the back side of the hotel, so it's very close. So There you go. How many used to come here? Well, some of them are too old to stand up, maybe. So anyway, I did like the food. The food was good. What I wanted to point out here, on October 2nd, we got a geologist, a doctorate in geology. We do have one chemical engineer. We have a doctorate in hydrology, and we have a civil engineer. This work is multidisciplinary. We can't do it just as chemical engineers. I think we can lead, but we need all of these disciplines. November 12th at the annual meeting, I'll chair a session, and this is what we're going to talk about. AICHE has a new policy. The old one was in 2014. Now we have a new one. Some people don't like it because it's not strong enough. Mary Ellen Turnus was the chair of the AICHE Climate Change Task Force in 17 and 18. She's going to talk about that. This gentleman is a professor of chemical engineering. He's going to, at Kentucky, he's going to talk about plastics and greenhouse gases. It'd be nice to turn a barrel of crude oil and a cubic foot of gas into something else. And when I first mentioned that to Mary Ellen, she says, oh no, not more plastics. So we don't want to do that. This is a gentleman that is associated with MIT and with Princeton. He is, has an engineering systems doctorate, and so he's going to speak. And then I'm going to close it. So that's what we're doing over there. Locally, as I say, we started a local initiative called Climate Solutions for Texas. We met in May. We're going to meet again September 26th. Contact me if you want to be involved. We have a lot that is going on. October 19th, we're going to have a table at the Houston Energy Day. Our section, South Texas section, is going to have a table, but also Climate Solutions for Texas. And also the Engineering Council of Houston. We're all under the same tent. And the Engineering Council of Houston, by the way, is very interested in what we're doing. They are supporting us in conducting a climate solution seminar. The Engineering Council of Houston is supporting us. I met with them today. And then at the spring meeting, there'll be another climate solutions session. I'm doing a little bit of an end around headquarters because, as I say, they have a lot on their plate, and they haven't really been that great of a resource to helping us grow. So at the annual meeting, I have requested chairs to let me come in and promote the climate solutions community. And I will do, right now I've got 13 invitations to do so. I want people to become involved in looking at issues that need to be looked at by multidisciplinary groups. Those are studies. I want to encourage other people to form local initiatives. And I do have a steering committee, and on the steering committee there are several who think that we need to have liaisons with every division and forum. These are the studies. None of them has to do with manufacturing processes, but they're all very important. There is a false view of renewables that it's going to save the day for us, but I have a colleague in Austin, doctorate in electrical engineering, who has spent his career on grid stability. Austin receives about 18% of their power from renewables, and they are at the ragged edge of instability, which means brownouts. So we'll never get to 100%. So that's one study. Another is baseload generation, which is either coal, gas, or nuclear, hydro if you're in the mountains. And then the last is the latest technology on nuclear reactor design, which necessarily involves fuel recycling, and also the elimination of all the spent fuel on the current nuclear reactor sites. So in the spring meeting, what I am considering and pitching to my steering committee is to have a climate solutions session on climate solutions for large industrial areas. I think that in the Houston area and throughout the Gulf, our industries can lead in this area. And the connection with nuclear, and this is important to me, is that we co-generate, and small modular reactors, SMRs, will be commercially available by the mid-2030s if we begin planning now. Our industry can lead in this area. I just want to point this out, and I'm going to show you in just a minute that headquarters is in line with us having a political stance. About a year ago, I spoke with Dan Crenshaw. I'm in his congressional district. He's the guy with a patch over his eye, and he asked me, why don't we use nuclear for base load? And so we talked about that, and there was a town hall meeting just a week or two ago, and he sent me this letter afterwards. He's a Republican. I hope he leads. Well, it's hard to believe, but this is an email from a lady who's on the AICHE Public Affairs and Information Committee, and she wanted to know what we do regarding government relations in our session, and I didn't think we did anything, and I learned that in previous years we had involvement. So it's interesting to me that they are encouraging that. When Climate Solutions Community launched in the spring, on March 31st, the AICHE issued a press release, and this was part of it. A key task assigned to the Climate Solutions Community Steering Committee will be to develop a portfolio of technical and government policy solutions necessary to address both industrial and societal challenges related to climate. So we've got the okay to get into policy. Of course, they want some oversight over that. Whew. That was all I had on climate solutions. I tried to get through it fast so we can get on to other stuff. Southwest Process Technology Conference. If you haven't registered for it, you're in luck. All those here tonight are going to get a break on the registration. I'll explain that in a minute. It's local to Houston this year, Sugar Land, so we're hoping for a big turnout. There are going to be 9 sessions, as you see there. One of them climate solutions. Our keynote speaker the first day is John Hoffmeister, the Shell Oil Company president, 2005 to 2008, and very, very concerned about climate change. And he's going to talk about energy transition. Joseph Powell, one of our section members, Shell Chief Scientist in Chemical Engineering, is going to speak at our October 1st dinner meeting addressing climate change and energy industry perspective. And October 2nd, Eric Kosman, president of the Society of Automation, is going to speak about automation. And we'll have an exhibition hall and a career fair. I had highlights going along here, and I forgot to pull them up. Okay, here's the break for all of you tonight if you haven't registered. Early bird rate ended August 26th for almost everyone, except for all of you. Just write down that code and go onto the site. You have to register by midnight on Monday, and you can get the early bird registration. So it's easy to remember, 2019 STS-EB. Okay, 2019 STS-EB. I'm going to continue here. All right, we need volunteers. One advantage of volunteering for this conference is that you don't have to pay any registration fee. And I got by with that for a couple of years. It's a pretty good deal. Now, David Solarski, where are you sitting? He left. Oh, he had that's right, he had car problems. Well, okay. This is what you would be doing. You'd either work at the registration table, you'd be a session aide for technical presentations, you'd assist exhibitors, you'd work the meals, collect tickets, and for doing one of those jobs, you'll get free registration. And this is the guy you need to contact, David Solarski, and STS-membership@aiche.org. So he does need volunteers, and it's a good deal for you too. These are our two sponsors. I'm going to get back. Where's Mark Harkness? There you are. Mark, I'm going to start beating the bushes for more sponsors, okay? If anybody wants to help me, Tom at tomream.com. I was telling Mark, I've got this piece of wood, not really, but, and every time we finish a dinner meeting, I put another notch in it, and it's almost finished. And then Mark is going to do it next year. But I'm going to lend him a hand on sponsors. But if anyone wants to help me, get in touch with me. Offshore Technology Conference. Tom Min is where? Where are you, Tom? Tom Min is the guy who organizes this every year, and he's done a bang-up job. There are, I don't know how many names there in that bottom paragraph, but he got enough people to volunteer and enough hours put in that the Offshore Technology Conference gave us $1,000 as an honorarium. That's the same as real money, isn't it? Okay. So thanks. Tonight we had two speakers, Jimmy Kumana and Trevor Rice. Jimmy is right here, and Trevor is over here. Thank you. And you have to come up because we're giving you something. Now, well, Carol, I didn't know you were going to be here. Carol and Dale handles the PE review course. Anyone else that works with you on that? Huh? Is it just you two, basically? You and Dale? You have other help?
The instructors.
Oh, the instructors, yeah, okay. Well, you and Dale are kind of the organizers.
Yeah, we coordinate.
Coordinate, okay. So another one is going to start in January, at the end of January. You can see it right there, University of Houston. If you go to our website, the bottom line there, just go to events and then go down to upcoming events. You'll see more details on the PE review course. I want to thank my executive committee. It's impossible to do this work for the section without them. Everybody that's here, stand up. Mark, come on, stand up. Eureka, Sheena, William, and I don't know if the others are here. I didn't see the others. Thank you. Now, we are giving scholarships to 3 very fine students. 2 of them are here tonight. And the first one on the screen there is not here. Her grandmother passed away just this week, so she's not here. So Katie, if you can come up. Are you going to help us, Sheena? Okay. I have to use the steps. Yeah, you're young.
Oh, the envelope's in here. I can pick the right one.
Whatever we're going to, I have to.
Yes.
And let's go over here where we can get on the film. So anyway, congratulations.
Thank you.
Okay. Job well done. Thanks you. Nicholas Sims. By the way, Katie was from Rice. I didn't know where you were from. I'm sorry. And you're from A&M, right?
Yes, sir.
Okay.
Thank you very much.
Congratulations. Now, we're going to have a holiday social this year. It's a mystery murder dinner. And the part of the mystery is we don't know where it is yet. But we'll figure that out. And just mark the date, December 5th. That's a Thursday. Now, we have a 50-year member with us today, Don Petrie, and William is going to do an introduction.
Dave received his BS in food technology in 1961 from the University of California and two master's degrees from Cal Davis in 1964 and 1966. These were in food science and chemical engineering, respectively. He studied at Stanford and MIT, but did not earn degrees from those institutions. He is a licensed PE in Texas. During his career, he worked at Phillips Petroleum for 27 years and the Continental Can Company for 2 years. He holds 2 patents and has authored 6 papers. During his career, he conducted extensive research on liquid mixing systems with multiple impellers and internal heat transfer plates in deep vessels. He worked on process design and support in North Sea operations platforms and in the Phillips EcoFisk complex. He also designed and operated a state-of-the-art continuous cell, single-cell protein pilot plant for the production of yeast and bacteria products. He was in the Air Force Reserves from 1958 to 1964 and was called into active duty during the Cuban Missile Crisis in 1962. He enjoys tennis and bowling and played a perfect game in 1979, and he participates in the Senior Olympics. Dave and his wife, Vicki, have 2 sons, 5 grandchildren, and 1 great-grandchild. And hopefully all that's still correct.
Okay, Michael, not yet, not yet. We give everybody a 10-minute break. So we're going to take about a 10-minute break, and then we'll come back for our the pop quiz. Oh, I'm sorry. I'm sorry. I promised James that he could make an announcement.
This will be quick. At the Southwest Process Technology Conference, October 2nd in Sugar Land that Tom talked about, we also have a session for current chemical engineering students. That's a Wednesday morning, and we like to bring in experienced engineers as mentors for 1 hour of that session. It's from 8:30 to 9:30 a.m. on that Wednesday. So if you're interested in being a mentor this year, please contact me or shoot me an email, james.turner@fluor.com, or I'll be around here during the break. Thank you.
Well, thanks, James. We have a lot of experienced people here, so you should get a good turnout. Okay, so we're going to take a 10-minute break and come back. Okay? Thanks. So we're going to start here in 2 or 3 minutes. People are starting to come back in, and two of our leaders said, "Hey, Tom, you forgot to put my slides in." So one of them is right here, Emily Jackson, our YP chair, and so she's going to go through about 4 or 5 slides, and then Matt Claudney is going to go through 2 or 3. So. Everybody, we're going to resume now. If you could all have your seats. Hey, Jimmy, have a seat. Okay, Emily Jackson, YP chair.
Thank you. I should be pretty quick. I always have to lower it. That's not going to change. Sorry, were you going to say something? Okay. I hope everybody had a good summer. If you have, just to introduce myself, my name's Emily Jackson. I'm the 2019 Young Professionals Chair for this year. So we're going to go through a few slides here and then hand it over to Matt like we had talked about. So we skipped one, a couple of them. Where are we at? Okay. So we typically start out with kind of events that we've had. Kind of our happy hour in May was at Lupe Tortilla, and we had a few faces show up. We would love to see any new faces, so if you ever run into any young professionals, wherever you're at, please let them know. I don't know why it keeps going.
I accidentally put in transition timing.
Oh.
So.
I wasn't ready for that, sorry. Please let them know we're going to have a happy hour, which we'll talk about in a couple slides the end of this month. We had our annual Astros game. It's always hard to get pictures at this game because we're rows of 20 people or so. But we had a lot of people show up. We're kind of all intermingled there, but you can see a couple of folks in the pictures that are here with us tonight. So before it moves, I'm going to have to kind of go back and forth because it's going to transition. Our YP of the month is Srihari Maganti. He is a senior process safety consultant at Brown & Root, an active member of AICHE National and our local section. He's currently our co-chair, and I'm going to make him come up here and get something. So come on. Thank you. He's got a lot of involvement from the young professionals to the Gulf Regional Representative, treasurer, co-chair. Thank you. And he has a PhD from South Dakota School of Mines and Technology. So thank you, Srihari. So as I mentioned a few minutes ago, we're going to have a happy hour in a few weeks, September 27th at Bovine and Barley, which is downtown on Main Street. 4 to 7 is typically our time frame. Drinks and appetizers on us. If you see anybody that you want to invite, bring along, please do so. And I wanted to let everybody know we do university outreach. We've already visited Prairie View A&M and University of Houston this year, and are planning a trip to Texas A&M as well as Rice for the fall. And would like, if anybody would like to join us, we're going to talk about networking, career opportunities, any industry experience. There's a lot of questions about industry experience and kind of getting your foot in the door. So if anybody would like to come along and join us, please let me know. And as Tom mentioned earlier, we have a murder mystery dinner on December 5th. So if you'll keep an eye out for an email and a location. So thank you very much.
Thank you, Emily. So one trick on Emily getting into the main presentation is to get me these much earlier. So let's see. Yeah, well, okay. Okay.
Let's see how we go forward.
This one here.
Okay,
Yeah.
thank you. Okay, well, thanks, everyone. We have 2 K-12 outreach activities coming up. I guess we'll go, let's see here. Yeah, the first one is going to be the Sally Ride STEM Festival, Saturday, October 12th at Rice University. And you can see the hours. Wait. Why does this keep moving? Okay, I'm the contact person for it. These are a couple of pictures. We get girls from basically middle school age, and it's great. You get to work with, here's from a couple of years ago. And then the other is Energy Day. That's the Citizens Energy Alliance, and it's going to be at Sam Houston Park downtown. The lunch and parking costs will be reimbursed. And this is the chair of the Citizens Energy Alliance, inviting our volunteers back to the event. Last year we had about 1,000 kids come through, and we had a great time showing them our exhibits. So anybody who's interested in either of those, please get in touch with me. Thank you.
Okay, thanks, Matt. Okay, so I'm going to put up the speaker's presentation and then introduce him here. Okay. What did I forget? I know I got it on here, Mike. There it is right there. It's on my desktop. Okay. So Mike Foggia came all the way here from Portland, but actually he came from probably somewhere else. He travels all the time. I'm going to be looking at my phone because I did a printout at home of introduction, but I forgot it. Mike Foggia is a business development and marketing manager for Process Combustion Corporation, based in Pittsburgh. He's out of Portland, Oregon. He spent more than 25 years with Roman Haas, now Dow, working in the specialty chemicals group, focusing on new product and process commercialization, technical service, sales, marketing, a lot of things for chemical and photolithographic technology applications. In 2006, he entered the air pollution control business, initially working on bio-oxidation technologies for the treatment of VOCs, and later diversifying into particulate removal, recovery, thermal oxidation, and scrubber technologies. Please join me in welcoming Michael Foggia. So you're familiar with that advance there with the arrow? And then that's just above it, yeah.
Thank you, Tom. First off, I want to thank everybody for coming out tonight. I'm going to give a presentation that really what we want to do is bring you up to speed. Most of you probably know the various technologies that are used for VOC treatment, but there are various technologies. There are a lot of differences between the various technologies, particularly when we're looking at the combustion or oxidation technologies. So what we're going to do is give a very high-level, brief overview of what these technologies are. So as Tom indicated, my name is Mike Foggia. I'm the Business Development and Marketing Manager for Process Combustion Corporation. PCC has been in business for 50 years. We're celebrating our 50th year this year, so we're very proud of that. We've been in business for a long time. We've built a lot of systems and designed a lot of systems over that 50-year time frame, many of which are installed in the Houston area. So there's a lot of PCC installations out here. So really today, what we're going to cover, tonight what we're going to cover is there's some basic things that you look at when you're deciding what air pollution control equipment or what technology you want to use. There's also some critical criteria that's pretty much applicable to most combustion or thermal-based oxidation technologies. Then we're going to talk a little bit about the primary technologies that are out there today. Non-recuperative and recuperative thermal oxidizers. We'll talk briefly about regenerative thermal oxidizers. We'll talk about an old technology that's really resurging into the industry. Today we're seeing a lot more activity of flameless, a truly flameless oxidation technology. And then a technology that's been around for many, many years, but is really starting to take off in areas where it's applicable, and that's a bio-oxidation technology. Our primary focus is the treatment of VOCs, so volatile organic compounds. Along with that, we have to look at NOx, SOx, we have to look at all the various offshoots and byproducts of combustion technology. But the technology's primary purpose is to put our customers or the end users in compliance. So really, when you look at APC equipment, there's one of the key things that you have to consider is the temperature at which oxidation or combustion is going to take place. It's easy to determine that temperature. You can look up the compounds. You take that complete list of compounds that are found in that airstream, and the first thing you do is identify what is the worst case. So what is going to be that highest temperature to achieve the destruction that you need? Now, the second part of that is then, okay, I know the temperature, but what technology, what system, what methodology do I use to achieve that temperature? And that's as critical, or probably more critical, than the temperature itself, because there's a lot of different ways of getting to that temperature. And nowadays, we have to concern ourselves with fuel efficiencies, NOx emissions, SOx emissions, greenhouse gas emissions. So the old days of just, a burner and burn it out, the flame in the can, there's a lot more that goes into it than did, 10, 15, 20 years ago. So really what you're looking at is you want to design a system that will oxidize, or a thermal oxidizer that's configured such that it promotes the total reaction of the air pollutants plus oxygen at an elevated temperature. And what this does is it results in total elimination of the waste compounds, and you end up with carbon dioxide, water, and some heat. So when we look at this, there are really three criteria we concern ourselves with. This is called the 3 T's of combustion, and they're common irregardless of what technology you're using. The first is time, okay? So how much time at temperature does it require for your oxidation reaction or your combustion reaction to take place? So very critical, very critical. Time is also critical because time is the primary element in determining the size of the system. And size relates to cost, as you can well imagine. The next is temperature. We talked about temperature, okay? You have to be at a given temperature, a temperature that's sufficient enough to promote a complete oxidation or combustion reaction. The third is turbulence or mixing. And in a lot of cases, this is the one area that is often overlooked, or not necessarily overlooked, but not as much emphasis is put on this. If we don't properly mix that waste gas, the air if we're adding supplemental air, the gas, natural gas if we're adding supplemental natural gas to it, if we don't get complete mixing of that waste gas stream, we're not going to have a complete oxidation reaction or a combustion reaction. And if we don't have a complete reaction, two things are going to happen. Number one, we're not going to hit our performance, so that destruction, that removal efficiency we're looking for. And two, we are probably going to consume more gas, natural gas, supplemental fuel, which results in a higher operating cost. So the 3 T's are really, really very critical: that time, temperature, and turbulence. So when we look at the basic design criteria for most thermal-based systems, you have a temperature of 1400 to 2200 degrees F. It's not often, unless you're using a catalytic oxidation system, that you're going to be below 1400 degrees. There are instances when you need to be over 2200 degrees. The average is probably in that 1500 to 17, maybe up to 1800 degree F temperature range. Residence time. When we look at residence time on most conventional technologies, you're going to find that the residence time ranges from a half a second to 2 seconds. So this is the time that you're in the combustion chamber, or you're in the area where the actual combustion or oxidation reaction takes place. Gas velocity, anywhere from 15 to 50 feet per second. Some cases we can go higher. Other suppliers, depending on their design and how their systems are set up, can go higher. But this is pretty much the typical range. To complete the oxidation reaction, you have to have a minimum of 2% by volume oxygen present. So if you don't have oxygen present, you're not going to complete that oxidation or that combustion reaction. So this is the basic design criteria that's utilized when looking at and designing a system. So, you need to determine that temperature. You need to look at how much time is it going to take to fully oxidize, to fully combust those compounds. You got to have oxygen present, and you got to make sure you've got good mixing. So this is applicable across all of the basic thermal oxidation technologies. A lot of this applies when you get into the biological as well. You look at it a little differently, and the operating parameters are totally different. You couldn't have a biological system operating at 2200 degrees F. There would be no bugs alive at that temperature, at least none that we work with anyway. So in the simplest of terms, what is a thermal oxidizer? And typically, when we refer to a thermal oxidizer, we're talking about the most common term is a direct-fired thermal oxidizer. So a thermal oxidizer is a thermal reactor where pollutants in a waste stream are heated in the presence of oxygen to a temperature sufficient enough to convert the pollutants to harmless compounds. Once again, carbon dioxide, water vapor, nitrogen, and oxygen. So when you look at this in the very simplest of terms, really what you have is you have a flame in a can, okay? You have a fuel source, you have a burner, you add supplemental oxygen, you bring your waste gas stream in, and you create a scenario where you're properly mixing that. Your combustion chamber, the flame, it burns into the combustion chamber. The combustion chamber is sufficient enough to give you the required retention time that you require, and then you exhaust to atmosphere. Okay? Very simple, very basic. They can be extremely complex. It depends on the compounds that are being treated. If you have very low NOx requirements, there are various things that you can do to the flame in the can, so to speak, to reduce the NOx. One of the big issues is they're not the most efficient in the world from a thermal fuel usage standpoint. And one of the reasons for that is you're not doing anything. You're generating a lot of heat, but you're not doing anything with that heat. You're not doing anything to capture that heat. So that's one of the areas. One of the big advantages of a system like this is you can achieve 99.99% removal efficiency. Very, very important. A lot of permits are written and require that 99.99%. When you look at typical applications, you want something where the waste stream is exothermic. So in other words, the waste gas typically will have a relatively high BTU value to it. So you're not supplementing it with a lot of natural gas or other auxiliary fuel. The stream can be wild in that there can be a certain amount of variation to that stream. A lot of auxiliary fuel is not needed. You're really not concerned with the materials of combustion. They can be loaded with particulate, they can be dirty. You just really don't have a lot of concerns for that. Fuel is typically not a major concern with the customer because they're going to either burn fuel or they're going to augment it with fuel. And due to the efficiency or the lower efficiency levels, the real concern here is removal efficiency, and meeting their permit requirements. So that's the typical. The systems can be in a horizontal or they can be in a vertical mode. There's a vertical mode depicted here with the burner at the bottom. As you come up through the system, this becomes your combustion chamber, and then you have a small stack on it. No real difference in efficiencies, whether you use a horizontal or a vertical system. It really comes down to footprint more than anything else. So that's a typical direct-fired thermal oxidizer. So now we keep in mind that we're evacuating 15, 16, 17, 1800 degree heat to the atmosphere when you're running a direct-fired thermal oxidizer. So what most people and most systems employ today are some sort of recuperative technology, whereas you take the waste heat that's being generated and you do something with that heat. The most common application is a waste heat boiler. Just about every factory out there uses steam in their process in some form or fashion. Most of them are burning natural gas to generate that steam. So if you take the waste heat coming off of a thermal oxidizer, you use that heat through a waste heat boiler, you now are, in essence, utilizing the heat to generate steam. You're able to either shut down that natural gas burning waste heat boiler, or you augment or add to your steam capability within your factory. So now you're utilizing that heat to do something else. Steam is the most common. You can preheat the air to reduce the delta T required to bring that waste gas up to temperature. You can have air heaters in the asphalt business, the roofing business. They use oil heaters to preheat the asphalt itself. So they're not using some ancillary heat. They heat oil lines, they put it into the vats of asphalt, and they heat it that way. So a tremendous number of uses for that heat, and there's a lot of different equipment out there. And once again, waste heat boilers are probably the most common that you're going to find on thermal VOC removal or thermal oxidation technologies. The typical application would be an application where the waste gas is either exothermic or endothermic. So you're really not as concerned with a high BTU value, because if you are supplementing it with auxiliary gas or auxiliary fuel, you're achieving a benefit from that. And that benefit is, once again, utilizing that heat to do something else within the factory. Obviously, you're not going to add a waste heat boiler or some ancillary piece of equipment there if the customer doesn't have a use for it. They're very expensive, and oftentimes a waste heat boiler can be as expensive as the thermal oxidizer itself, depending on the size and how much steam you're trying to generate. The application does not present an unmanageable fouling or corrosive concern. The obvious reason for that is you're using a heat transfer technology. If you have a lot of particulate or other compounds that will foul the thermal transfer capability of the auxiliary equipment, you're going to lose that heat transfer capability, and you're going to minimize the overall effectiveness of that heat transfer. So you want a relatively clean airstream and a non-corrosive airstream going into that ancillary waste heat recovery system. Fuel costs are a concern to the customer. They have a concern. They want to reduce the fuel. With this technology, if you are adding fuel, you're gaining value from every BTU of fuel you add to it. So it has a much higher payback. A recuperative system, once again, is the same as a direct-fired thermal oxidizer, with the exception you're recovering that heat. You will achieve the same removal efficiencies. These systems will produce and yield a 99.99% removal efficiency. Now, that's pretty much the max. Obviously, you can design a system to do whatever you need. I mean, if you needed 90% removal, you would design the system to do that. And typically that would probably be a lower retention time and possibly a lower temperature, but more than likely a lower retention time. But you will achieve that 99.99% removal efficiency. Typical that's a duplicate, sorry. Okay, the next technology is what we call a regenerative thermal oxidizer, or more commonly known as an RTO out in the field. RTOs are similar to a standard direct fired, but really what we're doing is we're capturing the heat and we're going to utilize that heat. And as a result, they're very, very thermally efficient. They're 95% thermally efficient. The best you're going to get, even with a recuperative thermal oxidizer, is maybe 80% heat recovery or thermal efficiency. Here, you're at a 95% thermal efficient. They're typically used for high volume airflows at low volume concentrations of VOCs. So typical applications most people would be familiar with, are paint booths in the automotive industry, where you have hundreds of thousands of ACFM of air being moved, but very low VOC concentrations, because there's a lot of scrubbing and a lot of recovery that takes place, but you do have low volume VOC. In the engineered wood products, your OSB, your MDF, your plywood, your particle board applications, once again, on the press and dryer vents, you have very, very high airflows, ranging from 100,000 to, I've seen it as high as 400,000 CFM, but you have very low VOC content. So these systems are a natural for that. They're very, very, very effective. So really, when you look at a regenerative thermal oxidizer, what you have is you have an oxidation zone, and your oxidation zone is basically a horizontal thermal oxidizer, so to speak. You have a flame, you're heating that oxidation zone or that combustion chamber up to a temperature that's sufficient enough to remove the compounds in the air. Let's say it's 14, 15, 1600 degrees F. This is where you start to get different from the more conventional systems. Now you have two zones that are made up of ceramic beds. They can be a block ceramic bed, or they can be what are called saddles, so just random pieces of ceramic that are put into the beds. These are heat recovery beds, so you're recovering heat and you're releasing heat, and that's what the purpose of these beds are. So once again, you're either going to recover heat or you're going to release heat, okay? The next thing you have are switching valves, and there's all types of switching valves used in regenerative thermal oxidizers. Probably the most common are called poppet valves, but there are indexing valves, there's rotary valves, there's all kinds of valves. But the key is it's a valving mechanism that switches the airflow. So you're going to directionally change the flow of the waste gas, and you're going to move it from one side to the other. A typical indexing or cycling would be in the order of 45 seconds to 3 minutes. And it all depends on the construction of the system, the compounds you're treating, the heat requirements, and what is the heat transfer capability of the ceramic media that you have in the system. So when we look at this, and we look at a flow diagram, if you look at the first, initially when you start the system up, you're going to preheat that ceramic bed in this case, in flow 1, so ceramic bed 1, which would be this bed here. So as the waste gas enters, the valve diverts the waste gas into the ceramic bed 1. That bed is hot, okay? It's probably 1,000 degrees, 900 to 1,000 degrees F, okay? What happens is your waste gas is at an ambient temperature, whatever that might be. So what we want to do is we want to preheat and draw heat from that bed, transfer that into the waste gas. So now we're elevating the temperature of the waste gas as it goes into the combustion chamber. So we may have that waste gas at 700, 800 degrees going into that combustion chamber, so you have considerably less delta T, or temperature change to reach the combustion temperature. Okay, the gas then exits the combustion chamber. Now it's hot. It's at 1,500 degrees. You now transfer the heat from that waste gas into the secondary ceramic bed. Now what you're doing is you're heating that bed up to that 900, 700, 800, 900 degrees. Okay, and then you come down and you go back out and you exhaust to atmosphere. So that's cycle one. Okay, now what you do on that cycle, which like I said, could be a minute, could be 3 minutes, it depends on the sizing and the total operation of the system. But now what you're going to do, you're just going to reverse this. So now we're going to go through ceramic bed 2, because that bed's hot. We cooled ceramic bed 1 down. So now this bed's hot, so we cycle up through here, do the same thing. We preheat that waste gas, bring it up to temperature, reduce that delta T. We come back out, we exit through the second bed, or bed 1 in this case. We heat that bed up to the maximum retention temperature that we're going to achieve. So we cycle back and forth. We cycle back and forth. This happens every minute, every second that the system is in operation, you're cycling on that 1 minute to 3 minute cycle. Here's the big issue with this system. You can get, most systems are earmarked at 98% removal. That's the common that you'll see. You're starting to see a lot of systems that will be billed at 99% removal. You're not going to get an RTO to do greater than 99% removal. It's just, it's not going to happen without, well, I guess if you added enough sections to it and had something that was just massive, you might be able to do that by capturing everything. But what happens with the system is, when you go through the valve, no matter what that valving system is, and those valves switch on about a half-second cycle. So when it switches, it's switching in a half-second, but you have enough waste gas that is exiting the system that's untreated, and that's called puff. Very common term, it's called puff. And there's enough of that waste gas exiting the system that you cannot achieve over 99%. So that's one of the downsides to the system, is you're not going to get, and believe it or not, you know, when I talk to people and you know, if you're in the business at all, you know, 99%, 99.9, 99.99, I mean, these are decimal points, you know, tenths and hundredths of a percent. But that's what permits are written at, and that's what's required. I mean, if your permit's written at 99.9%, you have to achieve 99.9 or better. So you have to understand that. And so when you talk about systems of these types and these 0.9s, it's critical. They have a place, they have a use, they have there's a need for them. So when you look at a typical system, once again, they can be in multiple cans. I mean, this is 2 can, then you've got 4 and 6. So this is 6 cans. And the reason for that is the volume of airflow. So as that airflow goes up, you add more cans to accommodate that. Otherwise, it would be so big, your back pressures and so on and so forth, and your flow through it would be so huge that you just wouldn't get the reactions that you need. So you do have to increase the system, and you use add cans to it, and it can be you start with 2, and it can be increments of 1 with each can that you add. So once again, you need to be a high volume, low VOC concentration. You have to have a clean waste stream. We have a ceramic media in there, it will plug. So if you have particulate, if you have silicon-bearing compounds, you can literally glass that media over. So it's got to be a relatively clean waste stream. It's got to be, for the same reason, a relatively non-corrosive waste stream. And you have to look at that and determine what the quality and the composition of the the silica and the silicone is within the ceramic media to ensure that you have the proper media in there. The other thing that's really, really important for a RTO is you have to have a very consistent waste stream. Not a lot of variation. So it's got to be pretty much the same volumes, the same composition day in and day out. And that's where the applications that they best fit. A wood products application is the same every day, minimal variation. A paint booth application, minimal. Believe it or not, RTOs are used in bakeries, treating ethanol alcohol that comes from the fermentation process and the baking process. They're very consistent. So those are some of the typical applications. So now we're going to get into, we've been talking flames, we've been talking, a flame in a can. No matter how you looked at it, it's burning. You're doing something with a flame. So there's a technology out. It's been out actually for probably 20 years plus. And there was a lot of activity 18, 20 years ago, 15, 18, 20 years ago, and then it kind of, due to acquisitions of the original company that developed the technology, it kind of got tabled, shelved, and now in the last couple years it's resurfaced. The president of our company was one of the co-developers of this technology back 20 years ago, and we have made some modifications to it. There are a couple suppliers out there that sell this technology. Not a lot of difference between the two systems, but there are subtle differences. But basically, what I want to do is just bring you up to speed on what this technology is from a very generic standpoint. So when really you look at it in the simplest of terms, a flameless thermal oxidizer is a refractory line vessel. So you've got a vessel that has refractory or an insulation in it, and it's filled with ceramic media. So the media, if you can see from the picture, that's a saddle media. Typically, it's a little higher quality, a higher grade than what you would find in a regenerative thermal oxidizer. So how does the system work? Well, first off, and the only time the system will actually see a flame is during the preheat or the startup phase. Okay, you have to bring that bed up to 1,400 degrees minimum is what the temperature that we like to see it at. So you have to have a flame to get it up there. I guess you could put electric heaters in, but they're much slower, much more costly, and are going to take probably a lot more time. So on larger systems, we use a flame. So you have a burner in the bottom, and basically you're just preheating that bed. Once that bed's up to temperature, you start the process. You turn that heater off, and you never turn that heater on again unless you've done some sort of shutdown. Because even if you shut down for a small amount of time, that bed's going to stay at temperature for hours and hours and maybe even days in some cases, depending on your operating temperature, because it's a glowing bed of ceramic, okay? One of the things that's done that really allows the system to operate and contributes to some of the key advantages this technology has is there's a utilization of a series of analyzers that pre-mix. So we pre-analyze and then we pre-mix the waste gas. So we'll look at the waste gas coming in, and you can throw anything you want at it. I don't care. You can mix everything in the plant and throw at it, or you can run 3 different lines, and today and tomorrow you run 4 other lines. Doesn't matter. Flow matters, but the composition of the waste gas doesn't matter, because we're going to analyze it, and we're going to either add air to it or we're going to add natural gas to achieve a known BTU value coming down the dip tube. We want that to be at a constant, and there's a very, very definite reason for that. So once again, we have an analyzer system, and that's really the heart and soul to this technology, is that upfront analyzer system, knowing what's in those compounds, adjusting them, and making sure that they are at a known set BTU value when they hit the reaction zone within the vessel. The gas mixture is below the flammable range, so there is no flame. It's not going to ignite. It's not going to burn. There will be no flame. We're oxidizing. We're not combusting. It's an oxidation reaction that takes place, and it's an exothermic oxidation reaction. So that's how we maintain the heat within the bed. That's why the burner is used to heat it up. Once the reaction starts, it's exothermic. You're generating enough heat from that oxidation reaction to maintain the heat within the vessel. Maximum temperature is 18 to 1900 degrees F. We don't go over 1900. We're typically in the 17 to 1800 degree range in most cases. Okay, so how does it work? Keep in mind now, once again, we're controlling the BTU value of that waste gas coming into the system. So as that waste gas comes down the dip tube, it hits ceramic media. What happens, because that's it's at an ambient temperature, it'll cool down. You'll cool that media bed, okay? So it's a natural cooling that takes place. But as that waste gas migrates out through that bed, it will start to increase in temperature because that bed is hot, and you'll hit what's called the oxidation zone, okay? And the oxidation zone is whatever temperature those compounds are going to oxidize at. Now, remember, I set the BTU value, so I know exactly what temperature they're going to oxidize at. I know exactly how far they're going to migrate out because I know the ambient temperature of that waste gas coming in, and I'm monitoring all the temperatures in the bed, particularly the lower part of the bed, and I'm monitoring the temperature of that waste gas coming in. So I control where that oxidation zone is, and that's critical because I want that oxidation zone to be maximum, so I have the maximum amount of surface area for that oxidation to take place, and I don't want it moving around within the vessel because if I move to one side or the other or up or down in the vessel, I'm not going to have a complete oxidation reaction that takes place, and I'm going to lose efficiency. So when we do the startup mode, this is just a little graphic just to kind of give you an idea. When we start up, whoop, the startup mode didn't go. Let's see. Okay, there it goes. So you start out with a cold bed. We have a heater, and we're going to bring that bed up to temperature. I mean, it's pretty basic. We're just heating up all that ceramic media within the bed. When we go into the operation mode, this is where you'll see the waste gas will come down the dip tube. It migrates out through that oxidation zone. You completely oxidize those compounds, and it's probably close to about as complete a reaction as you can get takes place in that oxidation zone. The rest of the gas then percolates up through that bed at 1800 degrees, so you have continued oxidation taking place. So anything that might be left, anything that was not oxidized within that oxidation zone will now be oxidized as it percolates up through the bed. And even when you get to the head space here, that head space within the vessel, once again, that's just like a retention time or like a combustion chamber. It's at close to 1800 degrees. So throughout the entire vessel, you have oxidation taking place or VOC destruction taking place. This is what the bed looks like. These are thermocouples coming down into the top of the bed, but it's just a glowing mass of ceramic media. It just glows. It's red hot, it glows, and no flame. So I was talking about feed forward, the controls, and the ability to handle multiple waste streams. In my way of thinking, and when I go out and talk to people, I'm finding that this is more important than a couple of the other things that advantages this system offers. Most major companies have multiple waste streams that they have to treat. They need a system that can handle this without having to do significant adjustments. A thermal oxidizer, you know, when your waste gas is coming in and you know what it is, you set a high temperature trip, you set a low temperature trip. If for some reason you hit it with some waste gas that has a high BTU value, what's it do? Temperature goes up. What happens? You hit that high temperature trip and it shuts down. Okay, now you got to go in, change that set point, account for that higher BTU value gas, or conversely, if it was a low BTU value gas, it's going to cool down. Then you have to shut down because you're not destroying the compound. So now you're in big trouble because now you're emitting non-treated VOCs. So because we use a feed-forward control system, and as I said earlier, we don't care as long as the flow doesn't increase. So if we design a system for 30,000 SCFM, as long as you don't vary much on that volume, I don't care what the compounds are, because I'm going to analyze those, I'm going to adjust those, I'm going to adjust those to the known that I want to complete my oxidation reaction. Hence, you have a system that is very, very efficient. We have a customer that they spend $6 to $7 million a year is what it costs them in lost product due to high temperature trips. And that's a tremendous amount of money. Now, when it trips, you know, they get it back online as fast as they can, but that's a lot of money. This system will virtually eliminate that with the feed-forward control on it. So, to my way of thinking, it's a huge, huge advantage.
Are the NOx controls pretty steady with this too?
Yes, and I'll go into that. Yes.
What kind of recovery do you get out of that?
What kind of what? Recovery of? Right here. We get 6 nines. 99.9999%. And if Will Huebner, the president and one of the original developers of this, was here, he would tell you it's 99.99997. You can't, and that's what we tell him. We kind of laugh and we go, Will, come on. Come on. You can't analyze for this. What happens is when you have a testing company come in, they pick up, it comes out as non-detect. And non-detect is as good as you can get. They cannot detect anything in that airstream at all. So that's typically what you'll see. Probably the biggest reason for that is, number one, setting up that oxidation zone and controlling that oxidation zone. But the other thing is, remember when I was talking about thermal oxidizers, we had a retention time of a half a second to 2 seconds. In this system, you have a total retention time of minimum usually of about 6 seconds. So you're significantly increasing that. So as it percolates up through the rest of that bed, any residual that's left behind is effectively treated and destroyed. So we will guarantee 99. Flameless thermal oxidizers will, no matter who builds it, they're going to guarantee 6.9 removal efficiency. They're very, very efficient. They're just a very efficient destructor of VOCs. So now let's talk a little bit about NOx, okay? Yakov Zeldovich, back, I believe this was like around the turn of the century, did a lot of work at looking at NOx, looking at thermal NOx, okay? I'm talking thermal NOx. I'm not talking chemical NOx. I'm talking thermal NOx. Did a lot of work, and one of the things he discovered was at 2300 degrees F, you exponentially increase the amount of thermal NOx generated, and it's a function of the temperature, okay? So how do we achieve less than 1 part per million of thermal NOx? And we will guarantee less than 1 part per million of thermal NOx. Well, if you look at a standard thermal oxidizer, you know, the burner in the can, that flame that's going in there, you may be operating at, say, 1,1700 degrees in the combustion chamber, but what's the temperature of a flame? It's all over the place. It's 3,500, anywhere from, I didn't even know what the low temperature would be on the flame, but you can go as high as 3,500 degrees. Now, low NOx burners have been designed and they're configured to bring those temperatures down so that you more efficiently control NOx, so you generate less thermal NOx. But no matter what you do, you're going to generate thermal NOx. Well, we operate at 1,800 to 1,900 degrees F. We do not exceed that. So there's virtually no thermal NOx created for all practical intents and purposes. Now, chemical NOx, that's the other NOx. The problem with this system is any complex nitrogen-bearing compounds. Because we're 99.9999% efficient, guess what we're going to do? We're going to make NOx. We're going to convert all those nitrogen-bearing compounds into NOx at a very high rate because it's so efficient. So we do not market the technology as it exists today, as we go to market with it for high nitrogen-bearing complexed NOx systems. Now, I suppose you could add an SCR and SNCR onto the back of this, but man, you're going to be removing a lot of NOx, so it depends on what those concentrations are. The other thing that I didn't mention is you can also add heat recovery to this. So on your exit, you could put a waste heat boiler, an air heater, so you don't have to evacuate or exhaust all that temperature to the atmosphere. But we do achieve, and we will guarantee, less than a part per million of thermal NOx. You have to look at the process when you get into the chemical NOx. This is a picture of a system that has been in service for 18 years. PCC didn't install this system. This was installed by the original manufacturer. But we do all the service work on this system, and we have been doing the service work for the past few years. It's a major pharmaceutical company in Ireland. What you see is the refractory. This is the dip tube. The black things are the studs that are used to hold the refractory onto the dip tube as it goes in. But this is what it looks like in the inside after 18 years in service. Nothing has been done to that refractory lining. Nothing. It's pristine white. And if you look at it, this is what 6.9 removal efficiency is. There's nothing left in that stream. If you looked at a standard thermal oxidizer, even at 99.99% removal, you're not going to see a refractory that looks like that after 1 year, let alone 18 years. So it's very, very clean, very, very efficient. So this is a picture of that system, the pharmaceutical manufacturer. It's been in business for 18 years. It's 14 feet in diameter, 20 feet tall. It's a very, very high flow rate. It's extremely reliable. And probably one of the key features here is, number one, when they permitted this, they permitted it as a reactor, not a combustion unit, not as a thermal oxidizer. And that helped them get their permit, number one, because of that terminology, reactor. Number two is, in the life of this system, they've probably changed their primary product mix 5 times. They've never had to change the set points. They're operating on the same set points today that they did 18 years ago. Multiple changes in processes, multiple changes in compounds going through the system. So that's key. The other thing is this system is located in the middle of dairy country. They need the 6.9 removal efficiency, and they're one of the few companies that needs that high removal. And the reason is, today they're making Viagra. And you can't have Viagra emitted out into a dairy field. Think about it, or don't think about it, whatever the case might be. So they need that 6-9 removal efficiency. It's very, very critical to them. So that's our little, we always like to tell that, and people kind of get a kick out of it. But for them, it's been probably one of the best air pollution control pieces of equipment they've ever installed. They have plans to install more of these systems as their requirements mandate this. But it's been a very efficient, very effective system for them. So, key benefits: 6-9 removal efficiency, less than a part per million of thermal NOx, low operating temperatures, so you're at a consistent, constant temperature, the feed-forward control. And, you know, where it's applicable, there are emission reduction credits, where because you're far surpassing the removal efficiencies and you're lowering your NOx levels down, you may be under your permit, and you may have excess credits or that you can sell, you know, in your area to a company that is not so lucky. So there is value for those credits. Okay, we're going to wrap up here with a few slides. We've been talking about thermal, we've been talking about heat, we've been talking about flames and heating up things to 1800, 1900 degrees. Now we're going to talk about Mother Nature. So biological systems have been around for 100 years, primarily used for odor control, primarily used for wastewater treatment facilities. They're still used today. The early systems were the size of football fields. So really what they would do is they'd dig a pit in the ground, they'd put an exhaust plenum into the bottom of it. Sometimes they humidified the air. Most of the time they didn't. They would pump the air through the plenum. It was covered with a bed of compost, usually a wood compost. The air would percolate up through it, and lo and behold, there'd be no hydrogen sulfide, that rotten egg smell. So very, very efficient for a while. First thing that would happen, the bed would start to compact upon itself, so now you have channeling, you lose surface to your media bed surface to airflow ratios. In the summertime, the bed's dried up, and you know microbes like to be moist. They'd get hot, so you're too hot for them. In the wintertime, they would freeze, so they go dormant. You don't kill them, they just go dormant, so you lost all effectiveness. So the key to making these things applicable for industrial applications was to take all that, confine it, fool Mother Nature a little bit into thinking that she's living in her world, but really we're controlling her world to the best of our capability, and come up with a system where we went from days, months, years for Mother Nature to do it to seconds, okay? So that's the key part. So what is a biooxidation system? Really, in its simplest terms, it's a multi-stage process where what you're doing is you're transferring the waste gas from the air phase and getting it into the liquid phase. Once you get into the liquid phase, it's just like treating any waste in wastewater treatment plants. Everybody knows that technology. It's very common with municipalities, industrial wastewater. If you can get it into the water, in most cases, you'll be able to treat it. So you do that either through adsorption onto a media film or through absorption into a water-based film. The primary element within the biooxidation system is the biofilm that's generated, and that's a living colony of microbes, naturally occurring microbes. These aren't engineered, they're naturally occurring microbes. Keep in mind, the waste gas is a food source, and if you think about basic biology, the microbes will speciate to the food source. So there may be hundreds or thousands of microbes in that system initially, but once you put the waste gas into it, the dominant microbes will be those that speciate to those compounds. So that's food. It's just they eat it, they digest it, they consume it. So water-soluble compounds are degraded in the liquid phase. Compounds that remain in the gas phase are then digested and consumed on a inorganic media, that has a high amount of surface area and grows a very thick water-miscible biofilm that the compounds transfer into and are digested. We do add a fertilizer, basically. It's Miracle Grow for all practical purposes. The microbes like high nitrogen, they like a high phosphorus content. So it's a good way of supplementing them because we want them to be as active as we can possibly have them. So in the simplest of terms, what happens is the air enters what we call the absorber section. The absorber section is water recirculating through a cooling tower media, very open-faced, large cooling tower media at about 1,500 to 2,000 gallons per minute. So you're really flushing that first chamber with a high volume of water so that we can knock out as many of those water-soluble compounds out of the air, get them into the water phase. When you go into the second phase, or the air phase, what happens is anything that is not knocked out into the water phase and transferred into the sump, and once again, the sump is very biologically active. It's basically a very, very super active, extended aerated wastewater treatment chamber. So we add air to it, we add supplemental media to it, and it's very active. So as we pass up through the second bed, it's a inorganic media that has a reticulated foam in it where we create a massive amount of surface area. So it's like a sponge with a lot of porosity in it. We create massive amounts of surface area for the biofilm to grow on. So here's the key to biodegradability. You can't treat everything biologically or we would use biosystems for everything. You can do it, but the system is going to be the size of the arena over here, and it would cost a fortune because you would need significant retention times. So when you look at your alphatic hydrocarbons, your methanes, your pentanes, your butanes, they go right through the system. You don't touch them. The key is the more water-soluble compounds. So if you get to your alcohols, your aldehydes, your ketones, your ammonia, your hydrogen sulfide, as long as they're not at levels that are high enough to be classed as a biocide and kill the bugs, these are the systems where you're very effective. You can get that 90, 95, 98%, 99% removal efficiency on these sort of compounds. So one of the key things is we compare this to an RTO. We sell RTOs, but we sell these systems as well. When you look at like a wood products application, either system can be used in this removal efficiencies. The key here is you're turning off the natural gas, which is 60% of the cost. You shut the natural gas spigot off, you're generating no NOx, 90% less greenhouse gas, no SOx. You're giving off a little bit of carbon dioxide, and the only reason you're doing that is because the bugs are alive just like we are. We give off carbon dioxide, they're going to give off carbon dioxide. So real cost advantage, particularly where the application makes sense. So this is how we like to close this presentation out. We talk about NOx removal versus total VOC removal. So we didn't talk about flares, but everybody knows what a flare is. I mean, they're all over the Houston area. The flame burning at the top of a stack. Those are tip flares. They're not real efficient from a total removal efficiency standpoint, and they're not real efficient from a NOx standpoint. They have their place, they have their use. There's a lot of legislation starting to take place now that flare manufacturers are going to have to modify and improve them, mainly because of NOx right now, but certainly due to removal efficiency as well. When you look at a biooxidation unit, there's no NOx, so it's fantastic when you get to the NOx, but because it's limited on the compounds you can treat from a removal efficiency standpoint, it's not the best technology. It's a good technology where applicable. When you look at an RTO, good NOx, but you do have that limitation on removal efficiency. You look at a thermal oxidizer, not quite as good as an RTO on NOx, but much higher removal efficiency. When you look at a flameless, it's probably the best of all worlds, as long as the compounds you're treating, meet the criteria. You get the high removal efficiency, you get the low thermal NOx, so it's a very efficient technology. We look at that as the underserved market. It's a market that we're educating, and the other suppliers are educating the industry into the capabilities of the flameless technology. So, like I said, there's been a resurgence of an old technology in the past couple of years, and it's really taken off. There are a lot more people looking at this for various reasons. And that's it. I thank you. Any questions? Yes?
The question is, what is the oxygen content of the effluent or the treated material going out of these thermal oxidizers?
It's going to vary. It's going to depend on what the compounds are. In a thermal oxidizer, it's going to be lower. In an RTO, it's going to be lower because you don't require as much oxygen present. In an FTO, excuse me, you do require more oxygen, 10 to 12% by volume versus the 2%. So you're going to have a higher oxygen level coming out. A lot of that's going to be oxidized during the heat, but it's going to vary really on the compound, so it's hard to throw a number out there.
So you couldn't use it as preheated air for a boiler or a gas stove or something?
You could if the compounds were right, and we've done that before. Once again, you just have to look at, it all comes down to what the compound loading is. What are you treating? Because that determines so much of what is going to be discharged through the system. Yes?
Couple of questions. So if you have a chemical stream that has nitrogens and sulfurs in it, which one would you recommend to mitigate the NOx?
It has what? Now, what were the compounds?
Like a refinery, if you have nitrogens and sulfurs in.
Probably, in most cases, I would recommend a thermal oxidizer, so recuperative or non-recuperative thermal oxidizer. They have the most flexibility, can handle the most diverse compound loading.
Okay. On your waste heat boiler in the thermal oxidizers, what is the metallurgy for that? Do you have any special metallurgy?
No, I mean, once again, it depends on what's going through it. I mean, they can be carbon steel, they can be stainless steel. I wouldn't, an Inconel would cost you a fortune, so you wouldn't see that probably. But most of them are carbon steel or stainless steel. And once again, it all depends on what's going through that system. If it's corrosive, you're going to have to go to a higher grade metallurgy.
The last question, if you have halogens in your stream coming in, you have to treat those before they go through the oxidizer?
No, we can handle halogens in a thermal oxidizer.
Periodically, you're going to cycle from ambient to 1800 degrees. Your ceramic saddles, are they likely to thermal degrade, break up with these big temperature swings?
Well, first off, the key to the system is we don't have any temperature swings, because once you heat that bed up to 1800 degrees, you leave it at 1800 degrees. You don't shut the system down. And if you did shut the system down, unless you're down for an extended period of time, the heat's going to remain, and that bed's going to be hot for a long time. So we use a little higher grade of ceramic saddles in the FTO than you would in an RTO. But no, 10 years is usually the lifespan for that media. The system that was 18 years old that I showed the picture of the refractory, they changed it at 10 years. They didn't have to. There was no degradation whatsoever to the ceramic. But they felt they had got their life out of it. They changed it because to be safe more than anything else. Be proactive. Yes?
Simple question. I've been involved with pollution control stuff over 30 years, number one. And in the process, we deal mostly in chemical scrubbers, wet scrubbers. We deal in NOx and SOx. How does the cost comparison between?
Oh, well, okay. A chemical scrubber, a pack tower chemical scrubber is going to be considerably cheaper, okay? But there's some problems with a pack tower scrubber. Yeah, you can hit removal efficiencies, but what do you do with the wastewater?
That's
What do
the
you do with the
problem.
water? You got to do something with it, because all you've done is knock the contaminant out of the air, put it into the water. And that's the difference between a bio-oxidation system and a pack tower scrubber. They're basically very similar, but you have an active sump. So you can discharge out of a bio unit right to the municipality. We haven't found a municipality yet that won't take the waste coming, the blow down coming out of a bio.
But usually in a chemical scrubber, the byproduct coming out is not a toxic chemical. You can discharge into rivers and stuff.
It depends on the scrubber, it depends on the application. There's some of them, it is toxic and they have to haul it off, or they have to do some sort of supplemental treatment before they can discharge it to a municipality. Yeah, you can do it into an industrial wastewater treatment plant, and you can go through all types of gyrations to remove metals and compounds that are found in that stream, and then discharge to the municipality. But you can't go directly from a scrubber to the municipality.
Last question, what is the limits of those compounds in the gas stream that you can use in a thermal oxidizer or
In a thermal, I don't know what the upper ppm level would be. Very, very high, I will tell you that. Very, very high. On a biofilter, you can't. You're limited to probably about 1,000 parts per million. But on a thermal oxidation system, I don't know a limit. Depends on the compound and how big you want to build it. It all comes down to retention time.
Thank you, Mike. We've run out of time for more questions. Anyone want to talk with Mike, he'll be here for a few minutes. So before you all leave, we're going to, well, first, Mike, stay here. We're going to give you a little gift. Let's give Mike an applause. Thank you.
Thank you.
I'm sure there are some treasures in here. I don't know what they are, but I appreciate you coming.
Thank you.
Okay, now we're going to see who knew the answers to the quiz. Okay, so if you had 1.7% increase from 2017 to 2018, which is an increase in energy-related CO2 emissions of about 550 billion tons, you're right. If you said that the percentage of CO2 emissions, energy-related CO2 emissions in 2018, which were stored geologically by carbon capture, was 0.01%, you're right. So let's see if anybody was right. Okay. No. Wonder how many no's we're going to get first. All right, let's see. No, that's another one. That one was 2.9 and 0.03. We're looking for 1.7 and 0.01. This is 0.5% and 0.02. If we get to the bottom of the barrel, we'll just won't have a winner. 1.7 and 0.03, half right, which doesn't give you anything. B and C, that's not right, because I know C was too high. Somebody was saying they're voting B in the letters. 1.7 and 0.03, not right. It's 1.7 and 0.01. 1.7 and 0.01. Hey, Vicky Petrie. Vicky. Oh, was that the? I think she's well. Gosh, what were the rules on that? Oh my goodness, I hate to take it to her house. No, somebody in our section lives close to her. Let's give her an applause. She's not here. Okay. So thank you for coming. Everyone drive safely. Our next meeting will be October 1st in Sugar Land at the Southwest Process Technology Conference at Sugar Land Marriott Town Square, or something like that. Okay. Thank you for coming. Drive safe.